So today we will discuss about how to design a Lagley compensator for a system using time domain approach. We have already discussed the designing of lead compensator and lag compensators using time domain approach. So here the problem is given as design a suitable compensator for a system having open loop transfer function that is equal to k divided by s into s plus 0.5 to satisfy the following specifications. The first specification is damping ratio is given as theta that is equal to 0.5 and undamped natural frequency of oscillation that omega n is equal to 5 radian per second and velocity error constant should be 80 per second. So we have to design a suitable compensator for this corresponding problem using time domain approach. That is our question. So how can we do that? So for that, first we have to find out dominant pole of the system. First we have to find out the dominant pole or dominant poles of the system, that is SD. That is equal to SD is equal to minus theta omega n plus or minus j omega d, where omega d is the damped natural frequency of oscillation, damped frequency of oscillations, and we can write it as omega d is equal to omega n into 1 minus theta square. By applying in this equation, we already know the values of theta and omega n. Our SD will be minus 2.5 plus or minus j 4.3. That is our dominant poles of the system. Step 2. Step 2 is to find the angle of open loop transfer function, that is theta p. Theta p at s is equal to sd, the angle of open loop transfer function when s is equal to sd. That we can find out using the equation k divided by s into s plus 0.5. Substitute for s is equal to this minus 2.5 plus j 4.3 and you can find out the angle. So if you find out the angle, that angle is approximately 235 degrees. So we will get the angle as not 235, it is plus 125 degrees. The angle will be plus 125 degrees. So while finding theta p is the angle of open loop transfer function at s is equal to sd, and that angle is plus 125 degree. And now you can see that the angle theta p is not equal to plus or minus 180 degree. That means the dominant poles are not lying on the root locus, and we have to design a lead compensator. Since the dominant poles are not lying on the root locus. So what is phi? Phi is equal to, phi is the step step 3 we have to find out the deficiency angle. Phi is equal to deficiency angle, that is 180 minus 125 degree, which will be equal to 55 degrees. Okay, the next step is we have to plot all this in a graph sheet. So you can see graph sheet here. In the graph paper, mark all the poles, open loop poles and open loop zeros of the given transfer function. Also we have to mark the dominant poles. So you can see that 0 and 0.5, 0 and 0.5, s is equal to 0 and s is equal to minus 0.5 are the two poles of the given system, and the dominant pole is represented as P. You can see that the dominant pole is represented as P at minus 2.5 plus J 4.3. Now from P we have to draw a horizontal line, mark that point as A. After that we have to find out the angle APO and bisect that. Find out the angle APO and bisect that angle APO. That angle bisector is named as PB. The straight line PB is the angle bisector. You can see there is a straight line, and that straight line PB is the angle bisector. Okay. Now from this angle bisector, mark 5 by 2, that is 55 by 2. It will be 27.5 degree in both the directions. Mark 27.5 degree in both the direction, and mark the point nearer to the origin, the point nearer to the j omega axis as 0 of the lead compensator, and the point that is far away from this j omega axis as take it as pole of the compensator. So in the lead compensator we got ZC is equal to the value of ZC is equal to minus 2.7 and PC is equal to minus 10. So we got approximately value of the poles and zeros like this. And if we write the transfer function of the lead section, okay, we write the transfer function of the lead compensator or lead section, we can write it as Kc into S plus 2.7 divided by S plus 10. Okay. So now that is the transfer function of lead compensator. Now we have to find that is step 3. Step 4, and now we have to find out, we don't know the value of Kc, but in order to find out the value of Kc we have to get the value of K, open loop gain K. We can see that our open loop plant have the transfer function, we can represent it as Gp of S, that have the transfer function K into K divided by S into S plus 0.5, and we don't know the value of K yet. So in order to find out the value of K, we can see that there are straight lines from all the poles of the open loop transfer functions and all the poles and zeros of the compensator. So draw straight lines from dominant pole, from the dominant pole P to the all the poles and zeros of the open loop transfer function and the compensator. So we already have S is equal to 0 and S is equal to 0.5, that are our first open loop poles of the given system L1 and L2. I can represent it as L1 and L2. Now at S is equal to minus 2.73 there is a 0 of the compensator lead section. There is a 0 of the compensator, that is for lead section. Okay. L3, and I can represent it as L3 and L4. So we have to mark all the poles and all the zeros of open loop transfer function and the compensator, and draw straight lines from dominant poles. Mark it as L1, L2, L3, L4, etc. Now, in order to find out the value of gain K, open loop gain K, in order to find out the value of open loop gain K, K is equal to product of vector length of all poles at S is equal to SD divided by product of vector length of all zeros at S is equal to SD. So K is equal to L1, that is the first vector length. L1 is the first vector length corresponding to the pole S is equal to 0, into L2, that is the second vector length corresponding to the pole S is equal to minus 0.5, and L4, that is corresponding to the pole of the compensator at S is equal to minus 10, divided by, you can see that there is only one zero, that is at S is equal to minus 2.7, that is a zero of the compensator, and its vector length is L3. Okay, so if you do this, you will get the value of K as 42.8. We can approximate it as 43. So that is our next step. So we got the plant as open loop plant GP of S is equal to 42.8 divided by S into S plus 0.5. That is our next step. Now we have to find out Kc. We have to find out Kc. Now we already have the open loop plant GP of S, and we got, by using the product of vector length, we got the open loop gain of the given system as 42.8 divided by S into S plus 0.5, and we have the GC of S, that is lead compensator, and that is equal to Kc into S plus 2.7 divided by S plus 10. Now how can we find out Kc? Kc is equal to, using the magnitude criterion, we can find out Kc into the open loop Kc into the GC of S, that is S into S plus 10, Kc into S plus 2.7 divided by S plus 10 into 42.8 divided by S into S plus 0.5 at S is equal to SD should be equal to 1. So what is this? Using the magnitude criterion. At the magnitude criterion, the open loop transfer function magnitude should be equal to 1. So now with the compensator, our open loop transfer function is GC of S into GP of S. So the magnitude of that open loop transfer function should be equal to 1. Now if you substitute in this equation, you will get the value of Kc is equal to 1.04, that we can write approximately as 1 or unity. So our compensator is now GC of S is equal to S plus 2.7 divided by S plus 10. Now we have some specifications corresponding to and the same specifications was theta is equal to 0.5 and damping ratio, undamped frequency of oscillations are 5 radian per second, and corresponding to that we have the dominant poles are corresponding to that specifications, but we also have steady state specifications. We also have a steady state specification, velocity error constant, and that velocity error constant is given in the question as 80 per second. Now we have to check that whether the velocity error constant, whether that specification, steady state specification, is satisfied. So in order to find out kV of the system now, kV of the system now, because with this lead compensator we can find out the kV using the equation limit s tends to 0. Now our open loop transfer function is this Gc of s into Gp of s, that is of the lead, Gc of s of the lead, that is equal to s plus 2.7 divided by s plus 10 into 42.8 divided by s into s plus 0.5. okay, s into. Now when you apply this limit, the steady state error will be kV with lead compensator, kV with lead compensator will be 22.7. we can see that the velocity error constant, of the system with our designed lead compensator is now only 22.7. what is our required steady velocity error constant? Our required steady state error constant is 80 per second, but we only got it as 22.7. that means steady state error specifications are not satisfied by designing a lead compensator. Other specifications like natural frequency of oscillations and damping ratio have been satisfied, since we have taken that dominant pole with respect to that specifications. But when you check, you can see that the steady state error compensator, steady state error value constant, the steady state error constant for this corresponding system have not satisfied. Since the steady state error the steady state specifications are not satisfied, since the steady state specifications are not satisfied, with lead compensator, we are going to design a lag compensator also. In addition to the lead compensator. That means you have to design a lag lead compensator for this corresponding problem in order to achieve the desired specifications, because with the designing of lead compensator itself, the steady state specifications are not satisfied, so we have to design a lag compensator also. That means the compensator here should be a lag lead compensator. The compensator here should be a lag lead compensator. So kV now, or kV of the lead kV of the system with lead compensator is now only 22.7. Now we are going to design a lag lead compensator. In that lead section we have already discussed. Lag section we have to discuss now. How can we design a lag compensator? So for that we are taking GC of S of lag section as Kc of lag. I am representing it as Kc of lag into S plus A divided by S plus B, and the Kc we will discuss, or the compensator gain we will find out it later. So now we will focus on to find out the transfer function Tf of lag section, the Tf of lag section. So that is A by B is equal to, that is A represents the 0 of lag section compensator and B represents the pole of the lag section compensator, that is equal to required kV required and kV of the system now, or now what is the kV of the system. Now we can write A by B is equal to 80 divided by, now what is the velocity error constant with the lead compensator? Now the velocity error constant is 22.7. So with respect to that we have to select A and B. With respect to that we have to select A and B. Now choose B very nearer to origin. So I am taking B as 0.05. Choose B is equal to a value that should be nearer to origin. I am taking it as 0.05 and our A will be, or 0 of the compensator. This is pole of lag section and A is the 0 of the compensator will be 80 into 0.05 divided by 22.7, that is equal to that is equal to 0.17. Now we can write the transfer function of lag section Tf of lag section as Kc into S plus 0.17 divided by S plus 0.05. This is Kc of or the gain of the lag section. Now if you remember the transfer function of lag lead section, you can see that alpha into beta should be equal to 1. Alpha into beta should be equal to 1. And corresponding to that, since Kc of lead section is approximately equal to 1, we can take Kc of lag section is also approximately equal to 1. So the gain Kc of lead and lag sections are approximately equal to 1, and we can write the transfer function of compensator, lag lead compensator as S plus 0.17 divided by S plus 0.05 into, that is the transfer function of lag section, into S plus 2.7 divided by S plus 10. That is our compensator transfer function. And when you check kV of system with lag lead compensator, we can write kV is equal to limit s tends to 0 s into limit s tends to 0, then s into s plus 0.17 divided by s plus 0.05 into s plus 2.7 divided by s plus 10 into 42.8 divided by s into s plus 0.5. This s and this s will cancel out, and when you apply the limit, it will approximately equal to 80 per second. So if you want, instead of 0.17, if you get the velocity error constant less than 80, I am getting the velocity error constant as nearly 79. So if you want to get it 80, we can rewrite this 0.176 as 0.18. If you rewrite it as 0.18, you will get the velocity error constant is approximately equal to 80 per second. So the first thing, in order to design a compensator, when a suitable compensator is given, first we have to find out whether the dominant poles are lying on the root locus. If the dominant poles are lying on the root locus, we have to design a lead compensator. And after designing the lead compensator, we have to check whether the steady state specifications are satisfied. In this problem, since the steady state specifications are not satisfied, we again design for a lag section or lag compensator. So here we have designed for a lag lead compensator, since the steady state specifications are not satisfied with only a lead compensator. So in these type of problems, you have to check when a problem is given, you have to check whether the steady state specifications are also satisfied. After designing the problem, you have to check that also. So now our compensator transfer function is s into, instead of 0.17, you can take it as 0.18. S into 0.18 divided by s plus 0.5 into s plus 2.7 divided by s plus 10. That is our compensator. Thank you.